Okay, welcome everybody to a new session of the Seminario of Álgebra, Combinatoria, and Teoría de Lie from Bahía Blanca in Argentina. And today's speaker is Gunther Cornelissen. He's an expert in several different subjects, including non-commutative geometry, number theory, mathematical physics, among others. And it's a great pleasure to introduce now that we'll talk about using the spectra of Twizy Laplacian to detect equivalence of Riemannian covering. Thank you, Gunther.
Yes, thank you. And thank you all for coming, and thank you for the invitation. Yes, if you have any questions or something breaks down or there is lag or so, just yell, then I can try to find the solution. I'm going to write on paper, so let's see how this goes. I wanted to start with showing you a diagram. And this is the starting diagram for the entire talk. And the diagram consists of two Riemannian manifolds. Let's always do closed, connected, smooth. Here's one of them. Here's another one. And I'm going to make the assumption from the start that they both map by finite coverings to something common. Let's say another such Riemannian manifold, but this can actually be, if you want, an orbifold, as long as the universal covering of this is a manifold. So we could put an orbifold here. Otherwise, just think manifold. And if you have such a diagram, you can basically do Galois theory with this, or as you like. You can find another manifold that covers this, but is given by a group action, group quotients. And in this case, both of these are finite group, and both of these are given by subgroups of G. So H1, M is the quotient, M1 is the quotient by H1, M2 is the quotient by H2, and M0 is the quotient by G. So this is my basic setup for the entire talk. In our paper, or actually it's now turning into a little book, there is all discussion about when this exists, when it doesn't exist, etc. But it is certainly, for now, an assumption that this situation exists, so that we have such a diagram. And this is the most famous, well, example is maybe the wrong word, of using this. If you have such a diagram, and if these groups, so it's purely group theoretical condition, are, let me call this weakly conjugates in G, I'll explain in a second, then what happens? Then you know that the spectra of the Laplace operators on these two manifolds are the same. And before I explain this terminology, let me actually say that this M1 and M2 are equivalent covers, so covering equivalent, if and only if this H1 and H2 are actually conjugate subgroups. So here is a strong condition. Here is something, well, it's called weak, so it must be weak. Let me actually explain this very briefly. Weakly conjugate, I think the easiest way to look at this is the following. You have these subgroups. These subgroups are not necessarily normal. Actually, if they're normal in G, then there's not a lot to do. But they have cosets, finite cosets. And on these finite set of cosets, the group acts by left multiplication, let's say. And this gives a representation. This gives a permutation representation. It permutes the cosets. And in the same way, G permutes the cosets on the other side. And the question is, are these, so these are G sets, and conjugacy would be an isomorphism of G sets, and weak conjugacy is just an isomorphism of these permutation representations as representations. And if you so want, if you know a bit of this group theory, this means that the induced representation of the trivial representation that I wrote here is isomorphic for these two subgroups. And this is the most convenient way of writing it for us. We will see a lot of these kind of funny symbols hanging around today. And the cute example of the cute observation here, the most important thing, is that there are examples where you can have weak conjugacy, but not conjugacy, so not covering equivalent, and actually even not isometric. Yeah. So here's a good example of not covering, well, this happens, I think this is due to Komatsu. You could take an abelian group of order p cubed for some prime p, maybe we just do 3. And you can take H2 to be the Heisenberg group over a finite field with 3 elements. So, I mean, a group of matrices like this, with these things mod 3. And these groups are weakly conjugate inside the larger one, but they are not conjugate because the one is abelian and the other one is not abelian. So, and this can all be used to actually construct, once you realize that, you know, you need to, if you want to make manifolds that are isospectral, but not isometric, you need to realize a situation where you have such abstract groups. So there's always some kind of story behind this of realizing a certain group or a certain configuration of groups. And we will also see this appear. So the main ingredient here is like there is this common quotient, finite quotient. There is groups hanging around. There is a certain representation theoretic condition. And there is a realization problem for the groups and the representation theoretic condition. And the way this is explained here, actually there's something historical behind this. And what is historical behind this is something in number theory. This is maybe cute to note because I see myself maybe as a number theorist. This goes back to 1926 when Fritz Gassmann used this to study the following problem. And you will see the analog of this diagram to the previous diagram. You take 2 number fields, so finite field extensions of Q. You take a common Galois closure, and you have exactly the same setup of groups. And now what happens is that the Dedekind zeta functions of these things are equal if and only if then you have a weak conjugacy. And the fields are isomorphic if and only if you have real, strong, whatever you want to call it, conjugacy. So this is where also the smallest, or the first example came from. Gassmann wrote this as a comment to a work of Hurwitz that was published after Hurwitz died. And here we see the first such construction. So this construction in manifolds, or actually this looking at these diagrams due to Sonada, is a kind of transportation of what happens here. But of course, you see, you have to bring in some kind of spectral geometry at some point to actually make this a thing in manifolds, so to speak. So let me say a little bit about that. So what are we going to do? We are going to start with such a diagram. So maybe I'll draw it again later. We're going to start with such a diagram, and we're going to add some material, some ingredients to it, and try to soup up this situation where covering equivalence is not the same as the weak conjugacy. So let me do this. We are going to do this by twisting Laplacians. So let me write down a little section on twisted Laplacians. And this is maybe best explained, and this is the only thing that I'm going to need by looking at, this is not the same cover we had before, but this is just an arbitrary finite group cover of such Riemannian manifolds. So you're given such a cover, and you're given a representation of G. So let's write this representation of G by complex matrices. And what you can do is the usual Laplace operator on M has a twisted version. The twisted version is twisted by the representation. So what is this? This is the Laplacian, but for the representation. And this is an operator, it's also second order elliptic, etc., that acts on a space. It actually acts on a space of functions that are vector valued on the cover. And the function vector valued on the cover, you see the small representation here. And this is because you're only interested in equivariant. I'll write a vector because it's n-dimensional valued. So I'll just write a vector for such a function on the top manifold and consider only functions that transform according to the representation. So let me briefly say something about this. Everything in the group and everything in the manifold. These are functions, which are a vector of functions of length n. And when you apply an element of this isometry group here to the manifold, to a point in the manifold, this vector of functions transforms by this matrix given by the representation evaluated at the corresponding group element. Yes, and so it acts on this. And how does it act? Well, it acts on this by spitting out another factor. Let me just write it like this. And this other factor is the usual Laplace operator on top, applied to f component-wise. Yeah, so f is just a vector of functions. On each individual function, you can act with the Laplace operator of m prime on functions, and you just do this component-wise. Representation and considering a representation of the entire fundamental group of M, not just this finite cover, but the entire fundamental group of M can be on top of this. And if you have a representation of the entire group that factors through such a finite quotient, you will get the same. And if you have a representation of this, then you can make, so to speak, Laplace operator of the universal cover act on the universal, on a bundle that on the universal cover is an n-dimensional bundle, and the functions that identify it are given by the representation, actually a representation inverse, let's say. But I'm not going to do that, so let's just forget about that and let's just do a finite group. I wanted to tell you one example, which is an untypical example maybe, but this is just if you have a 2 cover. So if you have a cover with group 2 and you take the so to speak, you take the unique non-trivial character, yeah, to the n is 1 case. If you do this, essentially what happens here is that the functions on top, they're kind of decomposed in even functions and odd functions. So this is what happens here. Even functions, essentially functions for, if I denote the action of this group by the generator of this group by minus, then these are really the invariant functions, and these are, so to speak, the exactly opposite, the odd functions. And functions that are invariant here, you can think of this as being just the functions downstairs, and the functions downstairs with the usual Laplace operator. And then here you have this funny space upstairs. Let's keep the notation. You have this, and on this one, you have the delta of this row, or actually it's a character, so we could write chi here. Yeah, so this is typically what happens. So in the top space, there is a copy of the bottom space for the trivial part, and then there is this funny twist part. Yes. So there were 2 ingredients in the proof. So we have this twisted Laplacian and we have this diagram. And what I'm going to write down now immediately is the main theorem. The main theorem says, assume the following 2 things. So a diagram, well, a diagram as we had before. So the diagram as before was really this kind of diagram, GH1, H2. And assume, and I'm not going to specify this now, but it's a condition on the homology representation. The homology representation, so this means that the group G acting by automorphisms on the first homology group of the top manifolds. Well, let's do with rational coefficients. I mean, actually, it will be mod L coefficients later. So there is a thing here. So I'll just give it a little color. This is a thing I will explain later. So there is a topological condition that we impose. This topological condition has something to do with being able to realize a certain group. But the claim is that if you have manifolds that fit into such a diagram and you have this condition, so this condition on actually this representation being large enough, then M1 and M2 are covering equivalence if and over M0, yeah, if and only if spectra of finitely many explicit twisted Laplacians on M1 and M2 match. So this is the, let's say, non-formula formulation of the main theorem. Yes, so here it is. You can actually detect covering equivalence. So in particular, you can detect, well, this is stronger than being isometric. It's like, so to speak, being isometric over M0. And you can detect this by spectra of finitely many explicit twisted Laplacians. It means I can give you a list of representations such that if you compare these spectra on these two sides, then after you've done this catalog of checking, you know that there is this equivalence. And it's even better. I mean, the theorem actually says that it's enough to check the multiplicity of 0 in finitely many spectra. So you will see this later. Yeah, before I say something about why this is true or should we believe it, let me actually do examples, or examples and non-examples. Maybe this is the best suggestion. So in the
famous
example of Heisenberg versus Abelian, yeah.
About the nature of this condition is
yeah.
You mentioned topological, right?
Mm-hmm. Yes.
I mean, if you change the metric on each of the manifold in such a way, you have still the diagram. This condition does depend on the metric or not?
No, the condition really only depends on the topology. It's really the condition is that you will see this actually. I prepared something to prove this.
Okay.
The condition is, I can tell you something now because this is maybe enlightening. So the condition is there to make sure that a certain group extension of G can be realized as an extra cover of the manifold M. And this is all that is needed. And the metrics that you will later use and induce on this coverings of the manifolds that give the correct twists, this will be induced later. Yeah, you can induce this later from the universal cover. But the problem is, if you don't, you can imagine, if you don't have enough covers, let's say you have no covers and M is simply connected, you are never going to twist. Well, you can twist by nothing. See, okay. So the topological condition is there. It's like inverse Galois theory. The topological condition is there in order to be able to make a cover with a certain representation theoretic property. And this is a topological condition. Yeah.
Okay, thank you.
Good. Yes, okay, good. Yes, example. I was just going to show you some numerics. So if you do the Heisenberg versus Abelian case, what you need to check, if I compute it correctly, is 522, well, for P is 3, 522 equalities. And approximately the dimension of the representation is approximately 10 to the 26. Yes, so maybe I said explicit, but let me not use the word manageable in this case. And the reason why Heisenberg versus Abelian is maybe very bad, I don't think 522 is so bad, but this is maybe bad. This is for some Galois theoretic reason. You imagine you need to be able to, you will see in the proof later that M needs to be extended to something larger. And you want this also to be Galois. And this is the typical thing that also happens in Galois theory. Galois closure can have factorial as many elements as this covering degree below. So this is I think one of the reasons. There's one example I wanted to definitely mention. I would always mention this, but in this audience it has to be mentioned. And now I will maybe misspell some of the S's and T's. Did I do this correctly? Anyhow.
Yes, correct.
Oh, very good. Yes. There is an example that for us was particularly interesting. It's due to Miatello and Rossetti. It's the following situation. There are two flat manifolds actually constructed explicitly by Bieberbach groups in dimension 4. And from our perspective, this is particularly nice because there's you will see this later. There's this complicated version of the group theory condition and an easy version. And this one doesn't satisfy the easy version, but it satisfies the complicated version. And the second thing is that these are isospectral for all twists by linear characters. So if you twist by one-dimensional representations, it doesn't help at all. So the theory here, the theory that we have, gives that you can fix this if you add the multiplicity of 0 matches in 18 equalities for 4-dimensional representations. So I can cook up for you explicit representations of dimension 4, and 18 of them somehow have to match in a funny way, and then you can actually see that these are not isometric from just looking at the multiplicity of 0 in the spectra of these operators. Yes, I mean, we have a whole list in the paper, but let me actually do a little bit non-examples. There are situations where you really can't use it. I mean, one of them is, for example, well, if M is simply connected, forget it. So if you take simply connected, well, they even exist in non-trivial families, manifolds, then you can't do it because there's nothing to twist. Also, you can't do Milner's example. Milner's example doesn't satisfy the topological condition. Condition doesn't hold. You also can't do these famous things of Vignerat. And this is because there is no diagram. And the fact that there is no diagram here, this has to do with commensurability and arithmeticity in this example. So this is also bad. So this is also bad. So there are various situations where you would be in a situation where you have, so to speak, the bottom of the diagram, or well, sometimes not. I mean, here you don't. But there is something wrong with the manifold at the top. You can't do enough twists. So here, for example, here also, this is too abelian, this construction actually. Yes. So there's a whole, you can do a few pages of examples. We also really try to do this and see what it looks like. Yes. So before I say anything further, let me actually say the topological condition. Yes, so this is the most general version. The most general version. Most general version says there exists a prime number, and I'll call it L throughout the talk, and L is co-prime to the order of the group G. So the group G was the group that is in the big cover. It should also be, in this case, larger than or equal to 3. And what we require is the following thing. So here is a permutation representation that we've seen before. This is how G acts on the H1 cosets. And this is a representation, it's a permutation representation. So defined over Z, it's by matrices with zeros and ones. And so it exists in any characteristic. And this one, we want to be a sub-representation. So a direct factor, sub-representation of this representation of G acting on the first homology of the manifolds, but now with mod L coefficients. So here you can just take Z coefficients and then just do everything mod L or tensor with FL. This is a representation in characteristic L, but L is co-prime to G, so this kind of behaves in a similar way to usual representation theory. Yes, so this is something technical. You will see later why this happens, but what I wanted to promote here almost is not the most general, but the most geometric version. So the most geometric version of this is something we call homological whiteness. Well, we also have a funny name for that, but homological whiteness. It's the inverse of homological triviality. It says that this representation, but in characteristic 0, so just over Q, this contains the regular representation of G. So that's something very concrete. There exists a homology class on this manifold, rational. Well, then also there will exist an integral version, such that if you take the orbit under all the elements of G, well, this is going to span the Q vector space, and the dimension of this should be the order of the group. So if this happens, you see the regular representation occurring in here, because this omega is a cyclic vector for the action. Yeah, so you really want the maximum number of independent things. So there will be, let's think a little bit about this not as homology, but maybe as geodesics or so. And imagine that you have a geodesic and then it's moved around by G and it gives you different copies. And what I want is really that these are disjoint, and they are still independent in homology. So this is what is the main geometric requirement, so to speak. Yeah. So there is the group of the top manifold. So the top manifold, remember, was here. This had this funny quotient to M0. And the condition is that this group acts here by isometries, and it will also act in the homology. And in the homology, it actually acts with, so to speak, maximal orbit. Yeah? So then it contains a regular representation. This condition, this geometric condition, implies that condition. Yeah? So if you have homological whiteness for Q, then you can find this. And this is in computation, and well, it's basically because of modular representation theory is the same in co-prime characteristic, and you can compute the multiplicity of this. Yeah, so we will get back to this a bit later, but maybe you will actually see this condition, or see why there is this funny condition, in kind of a sketch of the proof. Yes. So for now, I think it's kind of important that the statement of the theorem is kind of clear. So you have a diagram like this, and if you have a diagram like this and a representation theoretic condition, just think of this bottom condition. If you have that, then you can find finitely many representations to twist with here and here, such that if the multiplicities of zeros of these twisted Laplacian spectra match, then these are isometric, and even more, they are covering equivalent over this. So the groups that are here are conjugate in this group. Right. So what I wanted to do is actually like tell you the 3 main steps and why this is true, because maybe it looks a bit strange, like this suddenly this representation theory comes in, and why. So I won't call it a proof, but let me call it the section why. There are three things I wanted to say. So the first one is the following statement. This is just a very general statement. For all characters, chi I on the group hi, so just linear characters on these groups, you can detect whether or not they induce the same character to G. So this condition, representation theoretic condition, this can be expressed spectrally. Why? Why I will say later. How? Let's say the multiplicity of 0 in the following spectrum. So I take a spectrum on MI, I take a Laplace operator, and now there's a gigantic representation. So it's the complex conjugate of this character, and it's tensored with a restriction of the induction of the other labeled index. So what you see here is there is I indices and J indices, and the claim is that the multiplicity of 0 of these things is the same for any choice I, J equal to 1 or 2. Okay, maybe this looks a bit strange, so let's see, because this is the basic tool. This is a tool that was kind of known and forgotten in number theory. You can detect isomorphism of induced representations of characters by, well, in number theory, there would have been an L series here, but we now put a spectrum of Laplace operator of this representation. So here is a funny representation. Well, actually, there's 4. So you have the choices 1, 1, 1, 2, 2, 1, 2, 2. There's 4 representations. I claim multiplicity of 0 in all of these is the same. Then you have detected this isomorphism. Why? Well, essentially, the multiplicity of 0 in such a Laplace operator is the multiplicity of the trivial representation in the representation. So maybe I'll write this down. Multiplicity of 0 in the spectrum of twisted Laplace operator is the multiplicity of the trivial representation in the decomposition of the representation into irreducible representations. And this is also why, I mean, this is maybe the most interesting statement. This is also the dimension of the kernel of the twist. And if you think back, the dimension of the kernel of the twist, how was this defined? So this was defined as the usual Laplace operator of the cover, but the usual Laplace operator of the cover acts on a vector. And when do you have an element in the kernel? Well, you have an element in the kernel if you have a constant vector. So now the question is just, you have a constant vector. This is let me put a 0 because it's a constant vector. You have a constant vector and you want this constant vector to have this equivariance property, right? Because this is what we're computing in the space. So this is the actual kernel of the twisted Laplacian. The dimension is the number of vectors that satisfy this. Well, now you can get to this multiplicity of the unit representation from this kind of equation, right? If there's a constant vector here. So this is a very quick kind of reasoning why you could believe this. And well, the funny thing is, so this is the thing which is behind it. So you see here the multiplicity of 0 in this. And so what this tool here gives you is a way to convert this multiplicity equality into an equality of multiplicities of 1 in different representations. And then you manipulate this using Frobenius reciprocity. So you move this here and then you move that there, and then you can get to this result. Yeah. So this is pure representation theory with this little twist, so to speak. The twist that's here is to convert a spectral property into multiplicity of subrepresentation. Yeah, the next thing, and this is really group representation theory. So I'll promise I'll do some analysis, well, kind of analysis a bit later. We cook up a new group, and this relates to your question from before. So the topological condition has something to do with being able to realize the group that I'll now cook up. So this is a group. It's called the wreath product. I'll call it G tilde, and it's the following thing. I'm writing FL, but this is a cyclic group with L elements. It's a finite field with L elements, the additive group. Semi-direct product with the group G. And now I have to tell you how does G act on this thing well, it does so by permuting factors, base factors, like G permutes the H1 cosets. So this is a long sentence to parse, so let's write this down. If you have the H1 cosets or the H cosets, let's say G1 H1 blah blah blah, something GM H1. You remember G acts on this, an element of the group acts on this just by left multiplication, and it will change one coset into another coset. And I'll just, for convenience, I'll just use this notation. The change, the index, I call G of I. Yeah, so this is again a coset, a left coset, and which one is it? Well, it's the Gi. And if I do this, then what I mean by it acts on the base vectors is I take base vector for this vector space EI and do this. So this is how G gives an automorphism of this group. And this is called the wreath product. And why do we do this? Well, we do this because we pick this up from number theory, where this is used, and this is used in the following way. This is a theorem we used. It's from a paper I wrote with several authors, including Dr. Smith. Well, I'm really using L larger than or equal to 3 now. The claim is that there exists a character. This is a very special character. We call it solitary character. So I'll write big chi for this character on H1 tilde. Look, here's G tilde. G tilde is like this with G. H1 tilde is like this with H1 tilde, the subgroup where you put an H1 tilde here, etc. So there's a character here such that there exists a character on the other group, so on the H2 tilde, such that the induced character from H1 tilde to G tilde of this big thing equals or is isomorphic to the induced character from H2 tilde to G tilde of this arbitrary character. This is the same as H1 is conjugate to H2, well, tilde actually. in G tilde. Now, this is a whole mouthful, but let me actually explain what we have to remember from this. We have to remember from this that we were looking at arbitrary finite groups with subgroup H1 and H2, but what we do is we cook up a construction. It's this thing, the wreath product. It's here. We cook up the wreath product, and now the claim is that by doing this, I now suddenly can find a funny character on one side, capital Chi, such that as soon as I have the induced character by this one equal to one induced character on the other side, I've detected conjugacy. And this is conjugacy with everything with tildes, but you can, if this is conjugate with tildes, it's also conjugate without tildes. So what do we have to remember? We have to remember this is what we want. Yeah, because this is also the same as H1 conjugate to H2 in G. So we want this side. We see that, well, this thing exists, and we see that we should be able to detect by spectra this property. Well, now I think you are looking back at this first thing, because here is exactly that kind of thing, but now for the tilde groups, of course. So what do I want to do? This is changed into a spectral property by the first step, and down here is a statement that conjugacy, so covering equivalence, is such an isomorphism of induced representations. So there's one thing that we still have to do in this proof, and the one thing we still have to do is we have to show that we can actually twist, by characters on these tilde groups. Yeah. And so for that, we basically need step 3. So step 3 is realize a G tilde cover. And let me actually do this again by drawing the previous diagram. So, but only one side of the diagram. So here is our diagram with G and H1. And what I want to do now is I want to actually realize the wreath product. So I want to realize the wreath product by another cover, M tilde. This should be a cyclic cover with an elementary abelian L group as a covering group, such that this big group realizes the G tilde. And if I do this, well, I mean, this is going to be a corollary, but there will be a group here, and this is going to be an H1 tilde. And so what is my claim? My claim is that, well, this is actually a not to prove claim. If I can realize a diagram, so I can have a cover like this, then I can use all the previous tools to detect conjugacy of this group with another group in here. So there is still something hidden here, which is not so important for this construction, but there's still the second manifold here. Well, conjugacy of these things can be checked at this level by twisting with something in this covering of M1 and M2. And this follows from the previous two steps. So why? Well, the claim is that M tilde exists. So such a cover exists if and only if the topological conditions, either of them. And why? Well, we have two ways of constructing this. The one is just by fundamental groups. The other one is geometric. It's by fiber products. You can imagine that this cover here is not Galois, so you can act on this top cover with elements of G and get a kind of different covering maps. And you can take a fiber product of all of these with M and then go up to a fiber product with a cyclic cover of this. This is maybe too fancy, but there is a geometric construction and there is a construction just using fundamental groups. But the main thing to remember, so this is maybe the main remark for here, note, M prime over M is abelian. So corresponds to an element of, by the correspondence with fundamental groups, it corresponds to an element in the fundamental group. It's a cover, but even in the abelianized fundamental group. So it corresponds to something in this. And this should give you a hint that you need to have some property of this space that parameterizes abelian covers, such as this one, for it to be possible to construct this. And the condition that we need is this topological condition. Yes, so well, this is essentially the end of the construction. it's very explicit in the sense that you can actually count. You can count how many you need. You can count in terms of dimensions of abelianizations of these groups, and etc. And this is how you actually get the numbers. So if you run through the constructions, then you can just find the numbers. Yes, let me actually spend the next bullet on the topological condition. So the topological condition. I mean, maybe now you believe that this is a topological question. So the question is to realize this cover. And what you do then is like, this is all covered by the universal cover of M0. And this is a manifold, and you just push down the metric that you've put here, and you push it down to all these things, and then you get this required, all these things become Riemannian covers. Yes, so let me say something about this condition. So this condition is about the following thing. It's the group. The group acts on the homology. So this is, so to speak, a homology version of the group acting on the cycles or on the geodesics or whatever in the manifold. And let's look a little bit at, but this is representation theoretic, and also it's on homology, and the way geodesics get mapped to homology is not so well understood. I mean, this is something which is very different in manifolds than in number theory, let's say. So what I want to know is I have this representation. So this is an action. And I want to know, does it contain the regular representation? I'll just write greg for this. Well, let me tell you two examples. So the first one is, let's imagine the dimension of the manifold is 2. The Euler characteristic of the manifold is negative, and the action of G is free. Actually, there would be another case that we can do. You could take a Riemann surface of negative Euler characteristic with an arbitrary action. You could use the Eichler trace formula, but let's do this one. This is just topology, and this is always true. And it's always true by the Lefschetz fixed point formula. And the first time I saw this used in this way, I mean, there's a souped up version of this, but I thought it was really cute. So let's say this is the representation, and let's write psi for the character. The non-linear, let's say, the character of this representation. So the character is just a trace of the elements on this vector space. Well, the trace formula tells us something. Namely, if I take an element in the group that's not trivial, then it has no fixed points. And no fixed points is the left-hand side of the Lefschetz fixed point formula. And the right-hand side is the alternating sum of traces on the homology groups. Now, there's only H0 and H2, which are one-dimensional trivial action. So this gives a 2. And then there's left the trace of G acting on the first homology group. And this is what we called the character of G. And on the other hand, if G is trivial, then we don't do this, but we just do what is the trace of the trivial element on this? It's the dimension of H1, and this is 2 minus the Euler 2 minus the Euler characteristic. So if you plug everything together and you use that character as determined representations, you can also do the character of the regular representation, or the character of regular representation you know very well. And if we put this all together, you see that as a representation, this is twice the trivial representation minus the Euler characteristic over the order of the group times the regular representation. And maybe this is cute to contemplate briefly. We just have a formula for this representation on a two-dimensional manifold with a free action. And you can see here that if the Euler characteristic is negative, here it is. If the Euler characteristic is negative, then this representation just occurs. This made us very optimistic, but actually, let me just say one thing. As soon as you go up one dimension, then the world is wild. There is a result. It's due to Bartel and Page. It says that this can be any given G representation. So by this I mean, give me a representation of a finite group, then I can cook up a manifold such that the homology representation on this action is any given action that you want. So this is not going to be decisive, and And what we did was we did study some constructions, like you can do gluing construction. I picked up something from Cooper and Long, where you can take a manifold which has a simple closed curve that has a G orbit consisting of G, cardinality of G disjoint simple closed curves. You glue a copy of this to itself by erasing a small neighborhood of these closed curves, and then you get a manifold for which the regular representation occurs. And this is a topological computation that you can do. But you can also make a lot of situations where the homology is trivial. You can also look at symmetric spaces, and if symmetric space is rank 2, then you're done because it's a property T situation. But if it's a hyperbolic space, then sometimes you can find conditions at least on the occurrence of some automorphic representation inside the homology representation. It's kind of becomes a mess. I have no particularly good example of this. I would like to say that I think it's interesting to also look at mod L representation, so at torsion homology. And I just computed one such example, but this is modular representation theory, and it's a bit more fancy. Yes, I wanted to use the last section and the last few minutes actually to say one thing which I thought was kind of cute. I couldn't find in the literature, and it's about this. So I think in number theory we're used to working with zeta functions, and here we see results in terms of spectra. So are they really the same? So let's say if we have a symmetric second order elliptic operator and it acts on sections of some Hermitian bundle maybe on the manifold, then we have two concepts. We have the spectrum of this, so given by extending this to L2 and then just doing the usual spectrum, but we also have the spectral zeta function. And spectral zeta function is this. It's exactly summing over the non-zero spectrum, lambda to the minus s. Well, knowing this with multiplicities, and knowing this function is the same as knowing the spectrum of A without the zero multiplicity. So the question whether you could reformulate the theorem using zeta functions, just like in Gassman and in the number theory setup, where in the number theory setup, there is a result that fixes Gassman using L series of Dirichlet characters. And this is what we did in our number theory paper from a few years ago. What you see here is that this is not always the same information, interestingly enough. So I wanted to mention that. Do they mutually determine each other? So is this containing the same information as that, or said otherwise, is the multiplicity of zero determined by the non-zero zero spectrum? And I have three things to say about this. So the first one is the dimension of M is odd, then the answer is yes, and the answer is just because the multiplicity of zero is equal to the dimension of the kernel, and this is equal to minus the zeta function at zero. Well, zero, so this has to be analytically extended, and at zero it has exactly this value. But this is not true in even dimensions. So I was very stuck on doing this in even dimensions. In even dimensions, this formula has another term, and this other term is the integral of the local n/2 local invariance. So what about this? And this is actually false. And I'll show you an example. You can take a spin Dirac operator on a spin bundle, and let's write it like this, and look at these two operators. And I learned this from Nigel Hickson. Look at these two operators, same non-zero spectrum. And this is just because if you have AB and BA, you can prove this for matrices, basically. If you have AB and BA, the non-zero spectrum is the same, but you don't know anything about the multiplicity at zero. And what do you have now? Well, you have the index formula. And the index formula tells you that the multiplicity of zero in the plus minus the multiplicity of zero in the minus, this is equal to the integral of the A hat genus of the manifold. And I just wanted to show one example where this can be non-zero, namely 2. And this is 2 already on a quartic surface in CP3. So no, I was confused or mixed up in the even case, but in general operators, you can't really expect this zero multiplicity to be determined by the non-zero multiplicity. But then I actually got a question from someone and was able to prove that if you are not just any operator, but you're a twisted Laplacian like above, then I would like to say yes, if isospectral. So by this, I mean that this multiplicity of 0 in the spectrum is determined by the non-zero spectrum if you also know the zeta function of the usual Laplacian. And let me just say nothing except the final formula for this. This follows after some consideration. It's the following thing. I take the usual Laplacian at 0. I multiply with the twisted Laplacian divided by the usual Laplacian at the dimension over 2. It's even dimension. Actually, that's not even necessary here. And I subtract the value at 0, at analytic extension of the twisted delta. So here's a formula that tells you this multiplicity of 0 is determined by, and what is the data? The data is the usual spectrum, the usual non-zero spectrum, and the non-zero spectrum of the twisted operator. So I think so. I think this means that we are safe. Let's say we are safe in the situation of our main theorem with spectra in writing it with zeta functions if we add that the usual zeta functions also match. So if we add that the manifolds are isospectral.
Gunther,
okay, this is all. Yes.
What do you mean with twisted in this context? Because there is no any action here, right?
There's no what?
There is no G. There is no diagram
yeah.
in this context.
Sorry. So I'm just claiming that this is true if you are given such a cover and if you are given a representation of this group, then we have this operator that I was talking about, given this setup, right? And given this setup, if you have the twisted Laplacian on M and the usual Laplacian on M, that's this one, then the multiplicity of the twist at 0 is determined only by the zetas of this one and this one. But the usual one and the twisted one. Yeah, you have to imagine we're back in the old setting where I defined twisted Laplacian. Yes. Yeah.
Okay.
So that was this. Yeah. And then there is this funny formula that you can get from, I don't know, from various. I mean, this is a funny way to write the dimension of the representation. It's actually kind of strange. The thing that you need for this to work is you need to know n from the spectrum, and that's not so easy. But the n you can deduce from this. So there's essentially this is n, I think even. Yes. Good. Actually, that's all I wanted to say. So I'm in time, and I wanted to thank you for your attention already.
Okay, thank you very much for the very nice talk. Are there any questions? I have a question.
Okay.
In the list of non-examples, you include when M is simply connective.
Mm-hmm.
So you cannot put a sphere there. But what about a quotient of a sphere? It is also not valid for something with finite fundamental group?
Well, it depends on whether it can contain this group that gives this magical wreath product. So if you can, so you imagine here is the sphere. This is the universe. Let's say the universal cover is just a finite cover of the original thing. Your example is an example of that.
Yes.
So it really depends a bit on what this covering group is. Yeah. So I think if you are down somewhere with manifolds and you can realize still on top of this wreath product, then you're good. But you should be careful because I think, wait, there is maybe so what is a good example of this? A lens space is a good example of this, right? So you can, yeah. So in lens spaces, for example, this is actually not, I don't think it works because this covering is abelian. So you have this thing, it's abelian, and the entire thing should contain this wreath product that's not abelian. So there is always this, there is this kind of trade-off. So if I imagine if you have yeah, you should look a bit. I mean, I'm not sure what finite groups can you let act on an n sphere? I don't know. I mean, by
Well, there are
isometries,
many abstractions. That's the point.
Yeah. So right. So if you look in old, I mean, what is it? There's an old Milner paper, and there's all these lists of what can act and what not. You should. Let me say it like this. I think there might be situations where such a group occurs as an intermediate group. Yeah. So certainly this. I mean, if it's going to happen, then this wreath product group should occur somewhere for a quotient of your top manifold of the universal cover to a bottom manifold or orbifold. So it's kind of, it really depends. There is no general statement, I think, in finite fundamental group. It depends on the fundamental group, I guess.
Okay, so it might be the case that it doesn't work for any covered space by the sphere. Okay, by any spherical.
Yeah.
Okay.
Yes.
Okay.
Yeah. So for now, I can only say that for land spaces, I think if it's too close to abelian, it's not good. So yeah.
Okay.
Yes.
Okay. Are there any other questions?
Oh, Emilio, yes. Hi. No, I found very interesting the talk. Thanks to the speaker. And concerning the last section, I was very interested that maybe just to check the literature about examples of this situation is very interesting. I don't know if there are, but at least you know, it happened to me with isospectrality for the P spectrum, not for the functions, but on forms, to commit a mistake once that the two orbifolds, they were not manifolds, but orbifolds, two-dimensional, and they turned out to be one isospectral, but they failed in the zero eigenvalue. It was so we have some like four or five orbifolds. They were all isospectral for one forms, but one of them differ only in the zero spectrum, the zero eigenvalue. So the first.
Good.
So it's very interesting that.
Was there a topological reason for this? Because here, I mean, the example I cooked up was really this is just a topological invariant, which the A hat genus doesn't vanish, and then you get this funny multiplicities are not equal, but that's not what happens for you.
I have to think about that.
Yeah.
It's great that after all this general stuff that you presented, it's very interesting. Yes, I would have to read the paper because there is a long article. Yes.
Actually, let me promise cookies. We actually made it into a small book now with some more explanation. Excellent. So if you are interested in a version of that, I can email it around. So just email me, sure. Then I will send this version. And sure. I would also be very interested in maybe including that example, because I was, as I said, I mean, I was very confused for a long time about this multiplicity of zero versus not, and where could it go wrong? And it was very, actually, I think we ignored it for a year, and then we were very, very puzzled. But yes.
Yes. I think that
sounds interesting.
Okay. I will email you then.
Okay. Good.
Thank you. Thank you very much.
Any other questions?
I only caught the last 20 minutes, but thank you for a very precise lecture, introduction on representation theory, a very precise talk, and I'll look at that paper. Thank you so much.
Yeah, okay, very good. Yes, so if you email me, I can send you the book, so to speak. Yes, I think the main feature of the book is that it contains many open problems now.
My God.
Okay, if not, we thank again to Gunther. Very nice talk. Thank you very much.
Okay. Thank you.